Hey guys, we're going to continue where we left off, and that was with the least cost method. Right, so we had just finished a transportation problem, right, which is the one we had done for the northwest corner method, and that was the following, right, with the Apple stores in Hamilton County and the distribution centers in Ohio. So this was the final shipping policy we had obtained, right? And so before we go on and look at what the shipping cost was of this shipping policy and compare it to the result of the Northwest Corner method, I want you guys to ask yourselves the following question. Right? I want you to look back at the steps of the least cost method and try to identify how those steps, right, have as their goal to maximize the item sent from the source location to the destination location with the least cost per item for shipping. Okay, so I want you to pause the video, look back at those steps, and think about that question there. Okay, so if you're back from your pause here, these are the steps of the least cost method. Okay, and we can see in the very first step, right, this is probably the most direct way, right, we identify, or the most direct way in which this method tries to maximize this quantity, right? So this step immediately tries to find the cell, right, with the lowest shipping cost, which means the distribution center and the store, right? So that kind of is associated with that cell, right? And we identify that for allocation first. So we decide what value should go here first, meaning how much we should send from this distribution center to this store first, right? So the least cost method prioritizes that cell or this pair for which that cost is the least. So that's the most direct way in which that's the case. But a rather subtler, a rather subtle way in which this is also done in the steps of this algorithm is when breaking ties. Right? So we can see that if there's a tie between two cells, we don't just arbitrarily choose between them, right? Between two cells with, the same shipping cost per item. Rather, we take, right, and this was the clever bit. So we take the cell with the maximal minimum rim condition. Right, so we had a tie in this when we were doing this problem here, applying the least cost method to this transportation problem, and that was between these two cells. So at the time, this cell had as its rim conditions 10 and 40, and it was a 10 and 50. I think it was 10 and 50, right? And at the time, this cell had as its rim conditions 70 and 60, right? So we looked at the minimum rim condition for each of these cells. It was 60 in this case and 10 in this case. And we chose the cell with the maximum of those values. So we chose this cell, right? Because 60 is greater than 10. Okay? And in doing so, we're able to allocate more at this price immediately. Okay? If we had chosen this cell in that tie-breaking process, we would have only been able to choose 10 items at this price. Right, and that might have changed how many items we were able to choose at this price, right, for this cell. Okay, so we prioritized allocating the cell for which we were able to allocate more at that step, right? So we chose this cell because we were able to, ship 60 items at this price as opposed to only 10, right? So that's a subtle way that you might not have noticed how the least cost method tries to maximize, right, the exploitation of low shipping costs. Okay, so now let's look at what the total shipping cost was for this shipping policy, right? So we had 40 MacBook Airs going from distribution center 3 to store 1 at a cost of $40 per MacBook. We had 10 going from that same distribution center to store 2 at a cost of $2 per MacBook, so that's $20 total. We had 60. Am I missing something from this? I think I might be. This might not be the entire allocation. Yes, I'm missing 30 here. Okay. All right, so where were we? We had sent 60 MacBook Airs from Distribution Center 1 to Store 3 at a cost of $60 per MacBook. It's $120 total cost. Did I say 60? We sent 60 MacBook Airs at a total cost from Distribution Center 1 to Store 3 at a cost of $2 per MacBook, right? And then two more, we sent 10 MacBook Airs from Distribution Center 1 to Store 2 at a cost of $4 per MacBook. That's $40 total. And then we send 30 MacBook Airs from Distribution Center 2 to Store 2 at a cost of $3 per MacBook. That's $90. Right, so this is, let's see, 80, 100, 220, so 310. Okay, let me verify these numbers here. 40, 20, 90, 40, 120. Yes, so the total shipping cost for this shipping policy was $310. Okay, that's far lower than the $440 that was obtained from the shipping policy of the Northwest Corner method. All right, so it may seem like this algorithm is optimal, right? Because at every step we try to allocate as much as we can at the lowest price we can, but it's not, right? This is not an optimal algorithm. It is a heuristic algorithm, and that was stated in the statement in the original definition, or I guess explanation of the algorithm in the last video. All right, so the way in which cell values are chosen can actually force a very bad selection in many instances. So you might remember this is kind of what we saw in the case of the nearest neighbor algorithm for the traveling salesman problem. Right, so I'm going to give you guys a concrete example of this. Right, so let's use the least cost method to find a shipping policy for the transportation problem given by the tableau below. So this tableau contains all of the information of a transportation problem, right? There's no context, obviously, but from this point, we're able to apply any of the algorithms that we're going to look at to find a shipping policy. So let's look at the least cost method. Actually, but before we do that, really quickly, it's kind of evident that we would want to send as few of the resource or product being distributed from this distribution center 1, to Store 1, because that cost is astronomical in comparison to all other shipping costs, right? So maybe these two are in completely different continents or something weird, I don't know, or like there's a mountain range in between them, something like that. Or, there could be any number of reasons why this is much higher than the rest, okay? So a logical thing might be to supply all of Store 1's demand from the other distribution centers, right? Thus avoiding sending any at this price. Right, but the least cost method is an algorithm, and algorithms aren't necessarily adaptable. Well, this one isn't anyway, right? They're meant to provide a set of concrete rules where whatever situation you provide them, as long as the conditions for them to be carried out hold, right, you'll be able to get your answer. You'll be able to do it. They're just a set of fixed rules. That's the appeal of an algorithm. So they're not adaptable to these types of situations. I mean, maybe some are, but this one isn't. So it's not going to see this problem any different from this problem, right? It's not going to do anything special because of the two, right? Or at least anything outside of its set, defined, fixed rules, okay? So algorithms are kind of stupid in that way. But their brilliance is just in their dependency, right? And their explicitness. Okay. All right, so let's use the least cost method to find a shipping policy. All right, so we begin by looking at all not crossed out cells, right, which are all cells at the beginning of the tableau. And we look for the one that has the lowest shipping cost, right, which is this cell. Then we allocate to the cell as much as possible, right, which is the min of the two rim conditions, right? So it has as its rim conditions 3 for the row and 4 for the column, so we allocate 3. Why can't we allocate 4 here? Because then we would be oversupplying. And if these were flipped, say if this value were greater than this value, as is the case here for this cell, you can't allocate this value here because that would be supplying more than that distribution center can supply. So at most for a cell, the most that we can supply for a cell, or the greatest value a cell can have, is the minimum of its two rim conditions. So that's what we assign for this cell, right? We're trying to take full advantage of this shipping cost, okay? All right, so that's step 2. And then what we do is we actually subtract that value from the other rim condition, right? So that is step 2 of the least cost method algorithm. And then step 3 says we cross out either the row or column of this cell based on which rim condition was chosen. We chose the column rim condition, or excuse me, we chose the row rim condition here, so we cross out the row of that cell. All right. Then step 4 says, that was step 3, step 4 says we repeat that procedure for all not crossed out cells until we have one cell remaining. We have definitely more than one not crossed out cell left. Right, so we repeat that procedure, and that's the cells in these 2 rows. So we look at these 2 rows, and we find the cell with the least shipping cost, which is this one, right? And then we take its value, right? So that's step 1. We take its value to be the smaller of its 2 rim conditions. So in this case, it has rim condition 3 and 4. We take the smaller of those 2 is 3. Then we subtract this value from the other rim condition. That's step 2. Step 3 is to then cross out the row or column of that cell based on which rim condition was chosen. The rim condition of the row was chosen for that cell, so we cross out its row. And step 4 says we repeat that procedure now for the remaining not crossed out cells, which are these 3. Okay, so we select from these 3 cells the cell with the lowest shipping cost. Well, we have a tie here, right? And then we compare the minimum rim condition for each of these cells, but they're the same. Both of these cells have as their minimum rim condition 1. So I won't give you any problems where this is the case, right? That initial condition of the tiebreaker, comparing the minimum rim conditions and taking the cell with the largest of these, that should be enough to break all ties. But in this case, it's not. I won't give you problems like that. So, but in this case, it actually won't matter. So let's just choose this cell for step 1. Right? Then we choose its value to be the smaller of its 2 rim conditions. In this case, it has column condition, rim condition 1, row rim condition 4, so we choose it to be 1. Then we subtract that value from the other rim condition, so we get 3. And then we have 2 cells remaining. Oh, excuse me, right? And then step 3 says to cross out the column, since we chose the column rim condition. Then step 4 says we repeat this for remaining not crossed out cells. We choose the cell. Step 1 says, we go back to step 1. Step 1 says we choose the cell with the the least shipping cost. That would be this cell. We choose its value to be the smaller of its 2 rim conditions. Then we subtract that rim condition from the other one. And we cross out either the row or column based on what rim condition was chosen. Column rim condition was chosen, cross out the column. And then finally, we go to step 4. We have only 1 cell remaining, and the rim conditions for that cell are the same. We take the value of this cell, to be that. Okay, and we can see, yes, we were forced into sending the maximum, actually, amount of product that could be sent, or resource that could be sent from this distribution center to this store, which is highly, highly not ideal. Okay, so we use the least cost method, and we got forced into a very bad situation. Okay, so that just goes to show that the least cost method is not optimal. Although it can do very well, and generally better than the northwest corner principle, it can also do very bad. Okay, so in the next video, we're going to discuss Vogel's approximation method, which is the third and final algorithm that we'll use for solving the transportation problem that uses tableaus.